Hi, everyone. My name is Richard Yen. I'm here to talk about PG stats and about how Postgres and statistics work internally. It's a talk that's geared towards beginner and intermediate users, people who want to get an idea of how Postgres internal statistics operate and how it influences the query planner and how to improve their performance on some of their queries. All right, let's get started. We're going to talk about PG stats and how Postgres internal stats work. So many of you guys probably have experience working with simple queries like this easy one right here. Select star from customers where state equals California. Very simple. And, it's a table with customers and some information about the customer. And it's probably going to be, for simplicity's sake, we're going to make it very simple like this. So ID column, city, state, and the sign up date. And we create this table, we insert a million rows just to make sure that it might represent maybe the product that you're trying to work with. And we will have a index on both the city and the state column, as well as a sign up date. And if you have an index, we are most likely expecting that index to be used. However, when you run this, maybe you'll experience something like this. You'll see a sequential scan on customers, and you start wondering why. We run it again, and it's still a sequential scan. We do an analyze. We, try to do whatever dance we can do with the database, and it's still a sequential scan. Now, you might be tempted to think that something's broken, but it's actually working just fine. And we're going to talk about that today during our talk here. Um, the key point is that the query plans that you see, for example, like this one, these query plans, they are made by something called the query planner. Many of you are probably familiar with this, but I just want to reinforce this to you, especially if you are new to Postgres or just getting more deep into using Postgres as your database of choice. So this is the kind of layout that we would expect, or what we would see that your data lives in a customer's table, and when you select stuff, you're going to get data out of that customer's table. However, when the query planner does the query planning, it doesn't actually use the customer's table right off the bat. It actually gets statistics out of the PG statistic table, and that table is what gives the query planner an idea of what kind of plan it should use to actually execute your query. Um, the PG statistic table is actually basically like a summary. It's got a bunch of statistics about the table, the columns, some of the ranges, most common values, stuff that it could be that could be useful for the query planner to make that plan. And just to point out, the PG stats that we're going to talk about today is actually a view of PG statistic. So PG statistic is the table, and PG stats is a view of it. The reason why is because, the Postgres community who, that developed it, they wanted PG stats to be more PG statistic to be more human readable. And when you look in PG statistic, if you do a select star, it's actually not gonna be very useful to you. So using PG stats is gonna be your way to get an idea of what the query planner sees when it makes, a query plan. So, a quick aside, a little bit of Postgres trivia. So, if you have a table that has a plural, like PG stats, or if you have or a table or a relation that has the word stat in it, so like PG stat, user tables, PG stat, user indexes, those are all actually views, and they're not actually tables. The ones that are in the singular form are usually the tables. And you can see that if you wanna, run this query in, PSQL, and you'll see which ones are views and which ones are actually tables. Alright, so that's just a quick aside. Um, so how does PG statistic get populated? The way that happens is when you manually run analyze. So when you say analyze customers, it actually kicks off a process that scans your customers table, pulls all together all those statistics, and gets that summary into PG statistic. So we're gonna go through a simple example to kind of highlight what that looks like under the hood. Okay, so once again, we have our table, customers, we have our 4 columns, and we've inserted our million rows. We have our indexes, we run our analyze. What happens? So when we actually look in PG stats, so I just pulled 4 of the columns out of there. Attribute name, which is the column name of the table, n distinct, null frac, and correlation. So n distinct is actually the number of distinct values within that table. So or within that column, I'm sorry. So for example, like my customers are all based in the United States. So um, if I look at the number of distinct customers, distinct cities within that customers table, I'm going to see something like maybe 10,106. That's pretty reasonable. It's realistic. Um, I'm going to see 50 states, which is lines up with reality because there are 50 states in the United States. The null frac column is actually the fraction of rows that are null. And in this case, all the columns are not null, and the primary key cannot be null. So therefore, null frac is going to be 0. You might be wondering what the ID, why is it -1? So because every row in that table is unique ID because it's a primary key, there's going to be the number of distinct values is going to be the number of rows in that table. So that's why uh, Postgres lists it at -1. For correlation, this is actually pretty interesting. So when the analyze process pulls the data out of the database, the table, it assigns a correlation, and this is a statistical term. Um, it's if it's going to be between -1 and 1. Um, and the value of that actually affects whether or not the index scan gets selected. So for the way that it's calculated is basically like looking at how much data is on the disk. If it's randomly spread out, or if it's lopsided in one direction or in the other, the value gets assigned. So if it's going to be 0, it's actually going to be very randomly spread. So in that sense, it would not want to choose an index scan. It would prefer to do a sequential scan. So it's kind of like a penalty counter. So if the closer it is to 0, the more likely it's going to choose a sequential scan. The closer it is to the extremes, -1 and 1, the more likely it's going to want to choose an index scan. That all gets multiplied. There's a lot of math involved, and I won't get into that because this is kind of more of a introduction to PG stats. There's more information that's available online on the documentation. So if you want to look there, that would be a great place to start. Moving on, so let's actually look at some of the values that are in the PT stats table. So there's a column called most common vals, most common values, and most common frequencies. These are both arrays. So let's say you have a value of California, which is the first element of the array. The frequency in the most common frequencies is in that first value is going to be the frequency of the occurrence of California. So I'm pulling all that out and putting it into a table form here. You'll see that California's frequency in the table is about 17.4%. And in Texas, it's about 11.65%, and so on. So as you can see, the query planner gets these information. So if California shows up in the query, I want to select star from customers where state equals California. I'm gonna know that about 18% or 17% of my table um, is is populated with the state of California, and from there you can make some calculations. So I'm started talking about calculations, and the calculations are actually based on something called cost. So the cost of using an index scan or cost of using a sequential scan, all of these things are mathematically computed so that the query planner can choose, hey, it costs this much to do this, and it costs this much to do this other thing, and I would rather choose a cheaper one. The 3 costs, that we would want to focus on, there's a few other ones that are a little more nuanced, and I won't get into those, uh, just yet. I think these ones are the ones that are most people are, most interested in. So random page cost is the cost of pulling a random page out of the disk. So if I did an index scan and I find my value California and it says one of the tuples is in this page in this table, then I'm going to go randomly pick it. I'm going to go fetch that page out of the table, and that page fetch is called a random page fetch. So the cost of pulling that random page out. The sequential page cost is if I started at a particular place in the table and I pull the page out and then I pull the next page out and I pull the next page out, that would be what a sequential scan does. And it basically costs that much to do a sequential scan. Um, the CPU tuple cost is the cost of using the computer or the CPU to pull that tuple or that row out of that page. So I've done some page fetches and now I have the pages. I want to pull the tuples out. How much does that cost? So these are all tunable, and usually there are many guidelines online that we can reference that can help you based on your hardware and your setup, what the cost should be. Um, and that will be for another talk or exercise. So based on these costs, um, the uh, the calculation affects many different things for the query planner. It affects whether you choose a sequential scan, index scan, bitmap heap scan, and then when it comes to joining tables like the customers and orders tables, if you join those two, should I use a nested loop? Should I use a hash join or a merge join? All of these are calculated, and from those calculations, the query planner decides I'm going to pick the cheapest one and I'm going to execute it. So I'm going to move on and show you an example of how these cost calculations might affect the outcome of a query. So just like we started off with, we have a select on customers where state is California, and we have a select on the state of Wyoming, and we'll see how that gets affected by the costs. The output of the select on California, um, we see that the sequential scan, it costs about 19,000. Is the units are kind of there's not real units, it's just the cost of a query. Now, we know that there are 17,000 rows uh, estimated in the table. And then when it actually did the sequential scan, it found 17,200 rows, which is a little bit less, but it's still within the same ballpark. Now you can see that if I had 1,000,000 rows and 17 or 18,000 of those rows are California, it's about 20%, right? Um, yeah. So if you think about the idea that I'm going to do an index scan, I'm gonna scan through my index, I'm gonna fetch a page, and then I'm going to fetch the tuple out of it. I'm gonna move on to the next one, fetch another page and pull the tuple out. And you're going to do that 17,000 times in your 1,000,000 row table. That could actually take a lot of time and CPU cycles. So it might not be um, very useful to do index scans. So therefore, the query planner decides the sequential scan might actually be more efficient. Now imagine let's blow this up a little bit more. Let's say 900,000 rows have state of California. To fetch every entry in the index, you're gonna end up scanning almost the whole table anyway, so you might as well just scan the whole thing. So, hopefully that helps you understand and illustrate why the query planner chose to do that sequential scan even though it was 17,000 and 80, uh, yeah, 980,000 were still not the same value. Okay, so let's move on to the Wyoming example. Now, the Wyoming example, we only have 4,000 rows, right? So 4,000 rows, um, that is a significantly smaller amount of uh, rows in the database or in that table. So the query planner does a cost calculation and concludes, oh, 13,000. It's a bit less than 19,000. So I'm going to use the index scan now. And that's why it chose that. Now, you can ask, "Okay, how do I know if the query planner actually calculated the right cost? Like, how do I know that it's actually 19,000 and that's actually the fastest one? So what we can do is we can trick the query planner to say, hey, let's try really hard not to do the sequential scan. Let's try to encourage it to use index scan. So what we do is we can temporarily set enable sequential scan to off. And when we do that, we basically tell the query planner, hey, let's try very hard not to use this. Okay. And now when we actually do it, it does an index scan. And you can see that the cost here was 32,000. So it actually computed the cost that it takes to fetch a page out of disk and all that stuff. And it decided it calculated, hey, 32,000 is significantly higher than 19,000. So that's why the sequential scan is better. Okay. So, just basically to wrap up that idea, the most common values list, it really helps the query planner choose that sequential scan when that data is skewed. You have a lot more values of California versus very few values of Wyoming. All right, so let's move on. So we talked about most common values, and let's talk about histograms. So histograms are basically graphs of the frequency of a particular value or a particular range of values. So where state is equal to California or state equals Wyoming, those are equality, and that's pretty easy to get out of the most common values. But what if you wanted to look at like a range, like the customer signed up before January 1st of 2026, right? So that range is going to require a different kind of statistic, and the histograms is what helps you with that. Okay, so here we go. We're talking about histograms, and so the boundaries, right? So by default, Postgres will actually collect 100 buckets worth of information in for a particular column. So in this particular example, the sign up date, we have 100 buckets, and each of those buckets roughly comes out to about 2 months worth of data. So January to end of February, beginning of March to end of April, and so on. So this is good if your table is small or if you don't have a lot of variance in values. And I'm going to share with you this illustration of a histogram with low precision. So we have 100 buckets. In this picture, there's 5 buckets, right? 5 buckets from roughly about 5 to 32, and then 33 to 48. Now, this is pretty. I mean, I think it captures reality pretty well. I mean, there's most of your values are between like I don't know 48 and 63, but what it doesn't capture is the finer details, right? Uh, how what's your actual most common value? Or what if I wanted a smaller slice, right? So if you look on the picture on the right, the histogram has a lot more buckets and a lot more precision. You can actually see how infrequently the value of maybe 69 or 70 appears. Um, this kind of curvature won't get captured in that picture on the left. So how do we get more precision in our queries? Well, the way that we do that is by changing the statistics on that column. And with the way we do that is by altering table customer and altering the column, setting the statistics from 100 to 1000. So when we do that, we actually are now have 1,000 buckets, and each bucket actually, instead of 2 months, it represents 2 days. And this is actually gonna be a lot more precise, uh, and you might actually get a better query performance because you have better, statistics to decide what to do. Now, one thing I want to highlight is that there are trade-offs, right? Because when we have more buckets and you do an analyze on the table, you're gonna actually have to spend more time populating those values in that histogram, and you could end up with your analyze taking a long time. So that's why I would encourage you, if you need to change your statistics, do it on a table column by column basis, not on a wide scale. Now, I would like to move on to correlations, which is something that I think is actually very important, and some people might overlook. So When we are talking about our states and cities, right? So I want to select all the customers where city is Cheyenne and state is Wyoming. And you're going to get an index scan, which is great. But sometimes it might not be the right scan. So if you look at the row count there, what the what the query planner thinks is in the table that has city equals Cheyenne and state is Wyoming, it thinks that it only has 8 rows. And but when it actually runs, the actual rows is 4,000 because every city in that table that is Cheyenne actually happens to be with state Wyoming. The reason for this is because of simple statistics, right? The probability of choosing a city called Cheyenne and a probability of choosing a state in Wyoming, you multiply that permutation together, is the probability that you're going to get both of them in one row. Now, we know that in statistics that might actually work, but when they're actually correlated, that doesn't work because everybody who grew up in America knows that the only city in America called Cheyenne actually happens to be in Wyoming. So by when you select for Cheyenne, you're pretty much selecting for Wyoming. Um, a quick aside, I mean, there's actually one other city in Oklahoma called Cheyenne, but it's actually uh, population 700, so it's a very small city. I don't think that's going to affect our statistics here. But yeah, so the way to resolve that and to make that correlation, to make that connection, is by using the create statistics command. This is a feature that's been around since Postgres version 10. And the way that you call it is like this: create statistics and you name it, and then you want the statistics types. So we want dependencies and distinct, and you analyze the table right afterwards. The statistics type, you can definitely read more about that if you want, if you're interested in the documentation. Now, when I actually run this again, you'll see that the estimate is a lot more close. It's 4,087 instead of 4,012, but that's a lot closer than 8. So, um, while this example might not demonstrate that, if you have a large query which joins many tables and has a lot of correlation, you could run into the situation where one of these index scans, if it's estimated incorrectly, it'll affect the joins, the other scans upstream in that query. So we do want to make sure that our row counts are correct. So just to sum it all up, when you are dealing with queries, sometimes if it's slow and it's not behaving the way that you want, I have 6 steps that you can actually try to follow. So the first one, compare your estimated versus actual rows. So run your explain analyze, compare the estimated rows and the actual rows, and look for the deepest node. So if you have several joins, several tables that are involved, look at the very end of it and work your way up. Look for the ones where the estimate doesn't match with reality and see if you can resolve it there somehow. One way to resolve it is by checking your PT stats for that column. Look at the end distinct, look at your most common values, look at your histogram. Do those values match with what you know about your data? So for example, in my example, the number of states, like if it says only one state or if it says like 700 states, maybe that might be incorrect and might need to deal with it somehow. Now, if the stats look a bit stale, like maybe if it's like sign up dates or if it's um, some other value, uh, maybe you should run analyze. And I think this is especially true after a large batch load or migration, when more information is coming in and the statistics hasn't really caught up on it. The reason why the statistics might be stale, it could be because auto vacuum or auto analyze hasn't caught up, gotten around to that table to analyze it for you. So you might need to actually manually analyze it. Estimates are still off. Maybe you might need to increase the statistics. Like I mentioned earlier, Postgres by default captures just 100 buckets. You might need to increase it to 1,000 or more. Um, I think you can go up to 10,000 if you need to. Now, if there's a bad estimate that involves 2 columns or more, maybe consider the fact that they might be correlated. So you'll need to create extended statistics on that on those columns. Now, if all of those five steps of investigation don't seem to improve your query, after that, then you might want to consider maybe rewriting the query or looking for other ways to improve the query performance. So that wraps up my talk. I really want to drive home the point that the query planner is only as smart as the statistics that you feed it. So definitely be sure to keep those statistics accurate, analyze often, make sure you check and make sure those values are within reasonable ranges. So, really hope that you learned something new or got a lot out of this talk. And thanks again for joining us. And hope you enjoy the other talks at Posette.